Okay, now we're going to talk about the fundamental theorem of calculus. As you might guess from its name, this theorem is very important. It basically tells you the relationships between the two main things in calculus, derivatives and integrals. We know a lot about derivatives already, and we're learning about what integrals are, but the fundamental theorem of calculus tells you that they're related and lets you use one to find the other, which is great. So, let's remember what we have. When you see an integral like this, and remember f of t dt could be f of x dx or f of k dk, that's just that t is just whatever the input variable we're thinking about is. When you see this integral, that represents the net area between the graph of the function and the horizontal axis between these two input values, a and b. Okay. So it looks like this. There's our function, there's t equals a and t equals b, and that integral represents that shaded area. Now, if I change that upper bound to an x instead of a b, and I do that all the places there was a b, this is still the same statement. The integral from a to x of f of t dt is the net area between the graph of the function and the horizontal axis from a to x. Now, if you think about it that way, different values of x would give you different outputs for that. For example, if x is a point very close to a, that area would be small, so the integral would have a small value. If x is very far away, to the right here, then this integral would have a large value. So changing x changes what that integral equals. That means that that integral, is a function of x, right? You can think of inputting a value for x, you find that area, and that's the output. This function is known as an accumulation function. The idea is this tells you how area under the graph accumulates as you move from a to whatever point you're stopping at, x. And as you move x farther over, you accumulate more area. So this is an accumulation function. That's just what it's known as. And the point is it's a function of x. You input an x and you output this area. What's the derivative of this function? Right? Remember, the derivative of a function is telling you something about how this function changes if you move its input slightly over. The rate of change of this function. That is, how would the area here change when you change x? Okay, so here we have the picture again. And that area, remember, is the integral, which is an accumulation function, so I'm going to call it a of x. Right? A of x is just that area, that is that integral. And I want to remind you that the function there is y equals f of t. Okay, so what is the derivative? That was the question on the previous slide. What's the derivative a prime of x? That's a rate of change of a relative to x. That's how the area changes as you change x. But what's its official definition? Remember, this is the definition of the derivative, way back from when derivatives were first defined. The limit as h approaches 0 of a of x plus h minus a of x all over h. But what does that mean in this context? Well, x was already marked. Now I'm going to mark x plus h, slightly farther over. Now, h would be going to 0, so really these two values, x and x plus h, should be really, really close together, but so that you guys can see it, I'm putting them a little ways apart. Okay. So, what is a of x plus h? Well, using the definition at the top of the slide, it's just that integral, only instead of going up to x, we go up to x plus h. But that means that's the area starting at t equals a and ending at t equals x plus h between the function and the axis. That is the total shaded area, both the original blue part and this new little pink part that I've added. That's that total area from t equals a to t equals x plus h. whereas a of x is just the first original blue area. So now look back at the derivative formula. The derivative is the limit as h approaches 0 of, what's that numerator? The numerator is that total big area minus the original blue area. That's just the new added area, the little pink strip. And the denominator is still h. So a prime of x is this limit. Well, we can figure out what that area of the little strip is from our picture. Now, because x and x plus h are so close together, that little pink strip is almost a rectangle, so I'm just going to kind of level it off there. And what's that area? Well, it's height times width. So the height of that rectangle is, well, if you look, it's the y value is the function when you plug in the t value, x. So that's f of x. And the width is the distance from x to x plus h. That's just h. So the area is width times height, h times f of x. So back to the derivative formula, it's the limit as h approaches 0. The area of the strip is f of x times h. Divide that by h, and you just get f of x. Right? So what does that tell us? That tells us that the derivative of this weird accumulation function is the original function that we had graphed, f, only somehow we have switched from f of t to f of x. And the reason that happened is because when we made this a of x, the input variable is now x, because x is telling us how far over to use the area. And that is exactly what the fundamental theorem of calculus, part 1, says. If you have this accumulation function for a continuous function, and you take its derivative, you get the continuous function. In other words, this is the way it's usually written, the derivative of this integral is f of x. We'll see an example of using this in a moment. But for right now, I want to think about what else this means, how else you can think about what this says. If the derivative of this thing is little f of x, the derivative of this thing is f. That means this thing is an antiderivative of f. This thing, this accumulation function, is an antiderivative of f. And if f of x is a function that we know how to find an antiderivative for, that's great. It's some stuff plus a constant. And we could even figure out what constant it is because we have an input value where we know the output. That function, if you plug in x equals a, you do in fact get 0. Using that, and a little bit of algebra that I'm not going to go into here, we actually get an equivalent formulation, which is called the fundamental theorem of calculus part 2, which is more frequently used than the first version. What this says is, if you have any antiderivative of your function, then you can find this definite integral, this accumulation function, by taking that antiderivative and plugging in x, minus that antiderivative and plugging in a. And now I'm going to go back to replacing x with b, because we're more used to integrals from a to b instead of a to x. And I might as well switch the dummy variable just to have it look more like we're used to, but it doesn't really matter. The integral from a to b of f of x dx is this antiderivative with b plugged in minus an antiderivative with a plugged in. That is the second fundamental theorem of calculus, or the fundamental theorem of calculus, part 2. So now, an example of each thing. So first, the fundamental theorem of calculus, part 1. This horrible looking mess. Find the derivative with respect to x of the integral from 15 to x of 47 sine cubed of the square root of t squared plus 1 with respect to t. Lovely. Okay, it looks like what it's asking you to do is do this awful integral and then take the derivative of that with respect to x, and that is what it's asking you to do. But the fundamental theorem of calculus says you don't have to do that. All you have to do is take that inside bit that's inside the integral and change the variable to x from t, right? This is literally all that you have to do according to the fundamental theorem of calculus, part 1. Right? The fundamental theorem of calculus, part 1 says if you're taking the derivative of an accumulation function of f, the result is just f with the variable changed. This is amazing. This is like the best kind of math problem ever. It looks like you have to do all this hard work and you don't have to do anything. However, we do want to make sure we only do this when it's allowed. So what are the requirements to do that? Well, the function inside the integral has to be a continuous function. The lower bound, that's the 15 in this example, has to be a constant, right? It doesn't matter what constant it is, it just needs to be a number. And the upper bound needs to be whatever variable you're taking the derivative with respect to. So this has the derivative with respect to x, and that upper bound is the variable x, so that's correct. If all those three requirements are satisfied, then life is good, and the derivative of the integral is just the original function. However, that doesn't come up as much as the second part of the fundamental theorem of calculus. This lets us find integrals, compute the value of integrals without Riemann sums. So all that hard work of Riemann sums and limits and so on, we can avoid. Here's how. Let's compute the integral from -1 to 2 of the function 4x squared with respect to x. The second part of the fundamental theorem of calculus says all I need to do is take an antiderivative of the function involved, 4x squared, and plug in x equals 2, plug in x equals -1, subtract them, and I'm done. All right, so here capital F is an antiderivative of 4x squared, and if you remember it said any antiderivative of 4x squared. Right, so what is an antiderivative of 4x squared? Well, according to the power rule for antiderivatives, if you remember that, it's 4/3 x cubed plus c, right, plus any constant. But the fundamental theorem of calculus says what we're about to do works no matter what antiderivative we pick. That means no matter what constant we pick. We might as well pick the constant to be 0. So I'm just going to use the antiderivative 4/3 x cubed. So this integral equals, well, take that antiderivative and evaluate it at x equals -1 and x equals 2 with the subtraction. So plug in 2 minus plug in -1. Upper bound minus lower bound. And then a little arithmetic tells us that that integral equals 12. The value of that integral equals 12, right? And I did not need to do a single Riemann sum. I didn't need to draw a picture and look at areas and approximate it with more and more skinnier and skinnier rectangles. All I needed to be able to do was to find an antiderivative and plug in. Okay, so what are the requirements to be able to do integrals like this? Well, again, your function does need to be continuous, and it needs to be continuous the whole way that you're integrating. In this example, that means my function needs to be a continuous function for the whole interval from -1 to +2. That's the interval of integration. The only other requirement is you need to be able to find an antiderivative for your function. Now, a lot of functions, that's really, really hard, but for the next little while at least, we're going to be dealing with functions where it's pretty easy to find an antiderivative. If you can do that, you can do the integral this way, and it's amazing. So this is what we will be practicing. We'll be talking about how do you work with accumulation functions, how do you use the first part of the fundamental theorem of calculus, but most of all, practicing computing integrals using the second part of the fundamental theorem of calculus, that is, finding integrals using antiderivatives.